Okay, nice. I just launch. Okay, so nice to meet you, everybody. So today I talk about MiniF2F in Rocq. So it's an automatic translation between proof assistants. And so um, I'm just figuring out how to use my presentation. Okay, nice. So a recent topic that has gained momentum is to use large language models, LLMs, to do reasoning. So on the left, I showed you an example of some reasoning in natural language. However, with these techniques, one cannot ensure that the reasoning of the model generates is correct. So some people are looking at generating reasoning in proof assistants, such as Lean, Rocq, or Isabel. And, uh, and in the machine learning community, to evaluate some generation methods, one needs benchmarks, and especially benchmark datasets. And so that is exactly what MiniF2F is. It's a popular benchmark for code generation in proof assistance using machine learning techniques. It is made of 488 exercises from Olympiad, high school, and undergraduate math classes. So such as this one that I show you an example. And it's available in Lean, Isabel, and MetaMath, and unfortunately not Rocq. So in this work, what we want to do is to generate the Rocq version of the dataset. So we'll use the informal description and the Isabel and Lin versions that are already available. We use and we'll use LLMs to generate the Rocq version. And so by the Rocq versions, I mean only the statement of problems, not the proof that is done by that is made for other tasks. And so how we proceed? So first we'll use the four modem in this work. Some showcasing with the different characteristics. And as one may see, there is no open weight model. So we have to use them as black boxes. So that means that the prompt is our only lever for translation. So moving on, we'll do that with three stages of increasing complexity. So a stage is comprised of several steps, and a step is just an attempt by a model to translate all remaining theorems. So at the end of a step, we have human checking phases to ensure translated theorems are correct, meaning-wise. So for example, in this translation, the model introduced some parameter, airflow and big sum, and we don't want that because the proof is not doable with them. And so if, like in the later example, a theorem is considered incorrect, we put it back to be translated in the next step. Otherwise, it's considered correct and we won't try to translate it again. So let's dive into the first stage called one-shot prompting. In this stage, we give information to an LLM that output a Rocq translation, and we feed it to Rocq to see if this type checks. If it does, we move on to the human checking phase that will validate or not the proposed translation. So looking back at the first example I showed you, those were the informal description and the Isabel and Lin versions. And so a model successfully translated this problem at stage 1 and outputted this theorem, which is a correct translation. Looking at the results, we can see that at the end of the stage, we successfully translated about 68% of the dataset, showing that LLMs already possess strong capabilities to translate and generate Rocq statements. So to improve our results and performances, we design stage 2 called multi-turn with errors. And in this stage, we use the feedback from the Rocq type checking, our Rocq type checking tool. And the feedback we get from it is added to the prompt and feed it again to the LLM on the next atom. So we increase the number of atoms to 3. And so each time the theorem is not translated, does not type check, the error feedback gets added to the prompt and the LLM has a new try. For example, here we have a theorem using a pipe for division. For the division is for the divide predicate. And but this notation was not in scope, so that's not type check. And at the second atom, the model was able to correct itself by using a night point event. And at the end of so we focus only on 2 models. And at the end of this stage, about 80% of theorems were translated. And finally, we move on to the third and final stage, refine prompt. So at this point, at the end of stage 2, we noticed that some errors were pretty recurrent. For example, the models had a hard time using complex numbers or using the floor function, using a flooring function in general. And so our idea was to improve the prompt with a mini Rocq tutorial and some advices targeting the recurrent errors. And we also increased the number of attempts available to the model. And so, for example, as I showed you, before the stage 3, the model was like making up some unexisting libraries for complex numbers. After this, he was successfully using the Coquelicot library. Same for floor function. He used int part function correctly. And so at the end of stage 3, we end up translating 478 theorems out of the 488, which is 19% translation. And so we stopped here and translated the last 10 theorems by hand. So once this work was finished, we asked ourselves some questions, 3 questions actually. So the first one is, does a better model really performs better? Does changing the amount of information on the theorem changes the performance of the model? And finally, does the translated statement of the theorem make the proof harder to write? So for the first model, for the first question, which is a model comparison, we compared GPT-4o Mini and O1 Mini. So O1 Mini should be better because it leverages chain of thought reasoning. And so to compare them, we selected 100 theorems from 50 of which GPT-4o Mini had translated at stage 1, and we compare the model on a pass at 1, so it's one step of stage 1. As we can see at first, it appears that GPT-4 Mini is quite better than O1 Mini. So we increased the number of atoms, and so we did a pass at 3, where we accumulate the results of 3 steps of stage 1. And at this point, the performances of the models seem quite comparable. But we noticed an interesting thing that I highlighted on the table, which is that there is a notion of easy and hard translation shared by the two models. They tend to success and fail on the same theorems. Next, for the second question, we did an ablation study. Again, we compared the results of O1 Mini on Passat 1 and Passat 3 with different information in the prompt. So the one we did in our experiment with everything, only informal description, only code version, and only the lean version. And surprisingly, we see that giving only the informal description to the model yields the best results. And so it's quite strange considering that Lean and Rocq have pretty similar syntax. And so when adding the Lean version, so all remaining setup yielded approximately the equivalent results. And finally, for the third question, we did an audit. So we asked Rocq's users to review batch of theorems, and what they told us was that it was in fact a hard question, because what does it really mean, and because it's hard to figure out what it means, and if a statement makes you prove harder. It depends on a lot of factors and preferences. So we relied on their judgment. And for example, some of them told us that there were no badly written theorems, and some others told us that there were half badly written theorems. And the audit also stared for other things. For example, it helped us find unnoticed errors. So that was an example I show for stage 3, that passed at stage 3. And in this example, you see that there is a variable a of type q, and we want to prove something on the sum of the denominator and numerator of a. However, in Rocq, the denominator and numerator of an element of type q are not ensured to be relatively prime. So this statement could not be proven as it is, and we had to introduce the numerator and denominator ourselves and replace a. This audit also helped us better align with the informal description. So in this example, we want to show that the maximum value of an expression is 1 over 12. And the first translation was about only proving that this expression was was just less than 1/12. And so one Rocq user advised us to also add a part to the statement to prove that the maximum value was indeed reached. And so this is a problem that the Lean and Isabelle version are also subject to this problem. Finally, it helps us remove useless things or improve the syntax. So for example, here we can remove the useless import and the useless hypothesis of x and y being strictly positive. And we remove the square to just have a multiplication. So it's mostly about preferences of different users. And so for the results, so far we have the Rocq users audited about 150 theorems, which is about a third of the dataset. On this 150 theorems, there is only 2% of errors, 4% of reformulation, so that's minor error in the sense that it's about interpretation of the informal description. About 70% of syntax improvement and 77% of the theorems were already valid and required no changes. We also gathered proof for about 19% of theorems. In conclusion, the main lessons we draw from this work is that it's first the importance of feedback. We had a huge improvement by adding feedback in the prompt, and often the remaining errors in the 10 remaining theorems was that the model could not really interpret or understand the error message. So for example, in here, we see that the error message is talking about ENR of x plus y, and but in the statement, we cannot find it anywhere. So it's because the nat.add is replaced by a notation in the error message. And so it can alter the performance of the model. Moreover, in this work, we understood the importance of precise indication, targeting the LLM's default and limitation. So our work confirms the thing is that the less examples there is on internet, and so the less example available during the training of the LLM, the worse the LLM is in a particular field or domain. For example, it's quite good with natural numbers, but has a hard time with complex numbers. And so helping models in those fields can really improve their capacity and performances. So thank you for listening. You can help us by participating to the audit. You can contact us at llm4coq@gmail.com. And the dataset is available on GitHub and Hugging Face at those URL address.
Thank you.